Thanks everybody for joining. I understand this is a little bit of a different type of talk than most of you are used to hearing here at Devcon, and we actually wondered if it was even relevant or if you'd be interested in hearing it, but we're happy to see enough of you here to mostly fill a room. So at the end of the day, what we've brought here is hopefully not even something that you'll necessarily notice in your daily use of the Liferay cloud platform, if indeed you are a cloud customer, but it's more of the behind the scenes of how we've implemented and continued to iterate the Liferay cloud platform since we delivered it almost 7 years ago in MVP form. And as you well know, MVP code can be sticky. You have to iterate it and improve it over time. And so that's what we hope to show you today, is how we've maximized the accuracy of what you see on the cloud platform, minimized latency, and it's some of the most exciting work that we've been doing on the cloud platform.
So, hello everybody. It's a pleasure to be here presenting to you guys today. And before we go over the topics today, we want to have a little bit of understanding about your knowledge about some topics. So who here already knows about control loops? Have you heard about control loops before? We can have some interaction here. So if anybody has seen this topic before, has worked with this, you can raise your hand or say something.
We can see you, yes.
Yeah.
Very encouraging.
Awesome. Great. And how about Kubernetes controllers? Has anybody worked with this? Awesome. That's good. So we have some people in the audience that has worked this. That's very good. So I think we've selected the right topic, Jared.
Seriously.
Awesome. Cool. So I want you guys to close your eyes for a bit so that we can think about this together. I want to imagine that you are a LifeCloud user that is logging for the first time in the platform, in the Liferay Cloud platform. So as you log in, you are greeted by your project on Liferay Cloud. You see your services there. You see them turning from red to green to ready. And you see all of this information in real time happening. And you wonder, how does that all happen? How does my services actually run on the Liferay Cloud platform? How does this information that is visible to me, how does it get to me? How does this all happen? So this is what we will be discussing a little bit about today, and hopefully have everybody understanding about these topics. So, yep.
So as we sort of get started thinking on this mental journey together, I just want to check our vocabulary a little bit. On the front end, if you're familiar with using the Liferay Cloud Platform console, you're familiar with the services abstraction that we use, where you deploy your services, you build them and then you deploy them, and you've got a Liferay service and a database service and even a backup service. And these are all services when you're using the front end, but behind the scenes, we actually, on our team, we speak about them using the term workloads. So because we're talking about the back end, let's go ahead and start using the term workload instead of service. And let's also just work out a little bit of a definition for the term workload before we continue. A workload here, as we've defined it, is it's a resource running on the cloud, consuming compute and possibly storage. So behind the scenes, a service is a workload running on a Docker container, which is running on the cloud from whatever cloud provider we're using, which currently is Google Cloud. And that's what you're seeing when you log in. So when you look at the services UI, you can see there on the right, you're probably familiar with that front-end component there. You see here on the left that you've got a Kubernetes resource object. And this is what the definitions broadly look like on our Kubernetes instances running behind the scenes. And we use Kubernetes to orchestrate all of these workloads for you in order to run them behind the scenes. We leverage the Google Kubernetes engine to orchestrate all of these workloads in the Google clusters around the world. And we actually built Liferay Cloud Platform to provide these levers to you as the user to manage all of these distributed workloads within your projects.
Yeah, so let's dive a little bit deeper and understand about the platform. So what does Liferay Cloud Platform actually do? Let's go a little bit about this understanding. So a short sentence to understand what it does is it enables users to deploy, view, and manage their Liferay services as workloads on the cloud. Let's get a little bit more understanding about the meaning of these words, right? Let's focus on these three verbs here: deploy, view, and manage. But let's focus first on the deploy and manage. Let's try to get a little bit more of meaning to these verbs. Let's replace them with a verb that makes a little bit more sense, which is write. So the Liferay Cloud Platform enables users to write and view their Liferay services as workloads on the cloud. We have another verb here, which is view. Can anybody guess what word we could use for the verb view here? What word we could replace here with?
Rhymes with read.
That's it. That's it. So enables users to write and read the Liferay services as workloads on the cloud. That's great. Let's dive deep into this. So writing and reading the workloads on the cloud, there's a lot to it, right? It's not just a simple task. Well, writing is a little bit more simple, right? So when you want to write something to the cloud, when you want to create a resource, when you want to update or delete, you basically just send a request. So you click a button, the request is sent. So you send one request to deploy, one request to change, one request to delete, and that's it. At the same time, just in time, that request is fulfilled, and that's it, right? But reading is not that simple. It involves a lot of stuff, right? So it's hard. How hard is reading? So reading is hard because you need accurate information from the cloud. But your information on the cloud is constantly changing, right? So, and you will never know this until you send a request to read this information, right? So, for example, at 9 a.m., you send a request to read information from the cloud. So our API will go to the GKE cluster where your workloads are hosted. It's going to read that information about your workloads, about the state, how many replicas it has, if the replicas are running or not, right? And good, you get a snapshot of that information. But then, like minutes later, you send another request. Minutes later, that information might be outdated already, right? So we represented this with the clocks there, right? And you do not know if the information is outdated or not until you send a new request. So you have to keep sending requests to the cloud to understand the state of your workloads, right? So yeah, your information there might be outdated by the time that you send your request.
So let's just review that real quick just to make sure that we lock everything in. Liferay Cloud Platform writes and reads workloads on the cloud. Writing is easy. It's just one request to create, update, and delete the CUD of CRUD. And then for the R of CRUD, that's just a little bit harder because it's time-bound. So let's actually dive a little bit deeper now. I think we're all bigger nerds than just talking about CRUD. So let's dive a little bit deeper together and talk first just about a question that might seem off the wall right away, but we're going to dive into architecture in just a couple of minutes here. So we have to get this question out of the way. Why can't console just request state directly from Kubernetes when the user loads the page? Just to be clear, our Cloud Console front end does not just request directly from the Google Kubernetes engine in order to get that state. We actually do have a different architecture in place than just requesting directly. But let's talk about why we can't do that real quick. So the first reason is we just have a lot of users. And if you have a lot of users and they're all making requests, then we deduce that a lot of users equals a lot of requests. And the trouble there is that the Google Kubernetes engine, so far as we've judged, is not optimized for that level of read demand. So we need to come up with a different solution. Second reason is that the workload data as it exists, you saw it earlier, the workload data as it exists on Kubernetes as Kubernetes resources, it's really not easy to render that kind of data on a UI that's user-friendly, especially to people who aren't familiar with Kubernetes itself. So we have to transform that workload data into something a little bit more friendly for people to use. And also, if we wanted to make that data transformation, we shouldn't be saddling our front-end code with that data transformation. I don't know if you've ever tried to write a front end before that does a lot of data transformation, but you end up with really bad state management problems, and just it's heavy and difficult. And in my experience, it's just much better when your front end only worries about rendering data, and the data is already in the form that it needs to be rendered in from the back end. A third reason is that when you transform data on each request, this is just sort of harmonizing these previous 2 points, but when you transform data on each request and you have a lot of requests, that means you have heavy requests. And so if you think about this like fixed costs versus variable costs, if you have high variable costs, that means that every request just has a lot more overhead, and we're going to have a lot of latency. Users aren't going to be happy because they're waiting, they're clicking refresh, and things aren't happening quickly. So what architectural decision might we make in this case? You can probably guess that we're going to be using a cache. And more specifically, we're going to use a cache between the cloud, which is Google Kubernetes Engine for our purposes, and the front end, which is console. So let's draw a little bit of a diagram to understand what this architecture looks like, just so that we can kind of visually drink it in together. So there on the right, you have our rendering of the services page. So just imagine you've logged into console, you're looking at your services page, you've got your services listed, you've got a Liferay and a BusyBox, whatever a BusyBox does. And then here on the left, we've got the cloud. The cloud, behind the scenes, as you saw earlier, we've got our resources here. We have a deployment for each. Our Liferay deployment here is running 2 replicas, maybe one's a failover. And then here for BusyBox, we're just running a single replica. And then down here, we've got our cache. For our purposes, just to talk, we're going to use a MongoDB database. And that's going to serve as our intermediate state between the cloud and the rendered front end. And that's going to serve as our source of truth for the front end, for the console. And the magic then, the way that we connect this all together is we write a service to act as a liaison. In this case, we'll call it API. And this API will be able to fetch all of the workloads from the cloud, do whatever transformations are necessary, and then store those transformed abstractions as objects in our MongoDB database. And then that API service can also handle the requests from the clients, providing the renderable abstraction to the front end to make it user-friendly.
Let's review a little bit this architecture and understand this more in details. So we need a database, right? That will serve as the cache between the cloud and the console, right? The database will be the source of truth. So that means that we'll first read the data from this database to understand the state that is actually in the cloud. And one of the things that when we put a cache in there in between, one of the things that we must ensure is that the source of truth is in sync, is correct, has the correct data. Otherwise, you will be reading outdated data from there, right? So we must make sure that our database reflects what's in the cloud. It matches the cloud state, right? Cool. We have to cache the cloud in real time. So before we go deep into the solution that we chose for this, I want to understand from you guys again. So how do you guys think that we need to implement this pattern? So we have a problem to solve. We must make sure that the cache is in sync. What patterns come to your mind first when you think about this problem? How could we solve this?
Feel free to speak up.
Yeah. Let's organize it a little bit. Okay, don't try to speak all at the same time.
A hint is it rhymes with.
Yeah, it is polling. Polling is one of the ways you can do this. Of course, it's not the only one, but is one of the way that you can do this. And polling was the method that we chose at the beginning. So the Liferay Cloud platform was a very different platform at the beginning. We didn't have too many customers, right? So we didn't have too many requests. We were running on a different architecture before. We were running on Docker Swarm. So we didn't have all of the features that are available with Kubernetes. So polling was the natural solution for us. But how exactly polling works back then? So we have a little bit of architecture here, diagram for you to see. So we have this polling scheduler right there in the middle, right? So we have this clock to represent that this scheduler was running on a schedule. The schedule was 15 seconds. So every 15 seconds, our code would run, okay? It would go to each one of the clusters. It would list the workloads running into the clusters, and it would derive the state from the console, right? From the service. So as Jared explained in the beginning, we have a service, which is a concept of Liferay Cloud Platform, and we have a workload, which is the concept of the cloud. So we had to derive the state of the service from the state of the workload, and that was running on a scheduler, right? And what this was doing is, on every schedule, it was updating this cache and making this cache available to us, so that when the user requested the information about a service to us, we could go in and show if the service, if their services was running, was stopped, if needed more replicas or whatever that is. So that was what we used before, right? And it worked well for many years, but this design offers some problems that are difficult to solve, right? So is this solution scalable? And the answer is not. So think about this. Every 15 seconds, we are going through all of the clusters, all of the workloads. We are reading the data. We are deriving the state and all that. Okay. This is definitely a finite solution. And the way that we add more customers to our platform, we would eventually have to increase this polling schedule, right? Because it would just not fit enough the resources of the scheduler to be able to process all of the states, right? So as we add more customers, this solution would bring us some problems. And the problems relies specifically on the customer seeing outdated data. So while we were trying to process the state of the workload, right, the customer would see that their services was running, but perhaps it wasn't running, okay? So yeah, that's one of the biggest problems. But then comes to mind some questions, right? So when is polling the right solution for us to go with? When is polling is a good idea, right? So there are some patterns that if you identify these patterns in your problem, you can then safely use polling for that one. The first one is that data can be processed all at the same way. What does that mean? You have different types of data, different shapes of data, right? If you have that, perhaps polling will make your job a little bit more difficult. So if the data is more uniform, if they look like each other, it's more easy for you to use the polling mechanism, right? Also, when data changes happen at a predictable schedule. So I know that my data will be outdated after X amount of time. So, okay, polling is a good idea. I will put a schedule to work on that specific amount of time, let's say every hour, right? I will make sure that every hour I will run the schedule and I will update the data, do batch processing, whatever that is, right? But also when data changes are consistent, right? So if you have these patterns, that means that polling is a good idea for you. And for us, as we mentioned, it was at the beginning. Polling was the right solution for us because, yeah, we did have some of this stuff. But as the time evolved and as the need evolved, we noticed that this wasn't the case anymore. The nature of cloud is different, right? Because you have runtime data, and this data is constantly changing. Jared will explain a bit about control loops here in a bit, and you understand that. But basically, in the cloud, the data needs to be processed in many different ways. We have many different types of workloads. We just don't have like deployments, but we have stateful set. We have jobs, cron jobs. This data, they change in shape, in form, and way to be executed, right? Data changes are unpredictable. I'm running a pod now, and then a customer does like a deployment, for example. The state has already changed. I'm running a new version, or perhaps I'm running in the same version, but something happened, like the node scaled up or scaled down, and I needed to reallocate the pod, so the state will change, and it happens. And also data changes, they are inconsistent. So because of that reality, we were noticed with time to time that polling wasn't the best solution for us. And fortunately, we have ways to improve this and to go beyond it. And that's what we did.
Yeah, so at the beginning, we asked if people were familiar with control loops, and actually I only saw 2 hands, and those were 2 of the people that oversee some of our work. But I guarantee you that you are familiar with control loops, and we'll get into that in a second. And we'll get into how it connects to what we're talking about with Kubernetes here. So first of all, what is a control loop? A control loop, it makes a desired state into an actual state. That's all it does. You tell it what you want, and then the control loop, the entire job of the control loop is to make what you want come to pass, come into reality. And I think an example of this that hopefully everybody is familiar with, especially in the summer, is a thermostat. You put in some desired state, and by the way, I'm American, so I don't think in Celsius, but I did it for you. 20 degrees Celsius, we want our thermostat to keep this room at 20 degrees Celsius. The thermostat will run a control loop. It's a closed control loop. It checks the temperature on each loop. If that temperature deviates from the desired state, if it's low, then we turn off the air conditioner and turn on the heater. And if the temperature is too high, then we turn off the heater and we turn on the air conditioner. And then go to 1. Just continue to loop all the time. That's the entire job of a thermostat. And this has to do with Kubernetes because a Kubernetes controller, which is the heart and soul of Kubernetes, does the exact same thing. The input is not a temperature, it's a manifest for a resource. And the Kubernetes controller just makes that manifest match the actual state at all times. That's its entire job. And it's very lightweight, actually. And we can actually hook into this we can interact with the existing control plane there on Kubernetes and actually hook in and run custom code, which is a big deal when you consider the fact that we might have our own applications that we might want to use this for. And we can use Kubernetes controllers to do that. We can actually write our own custom controllers. And the reason why this is magic, and I'm going to draw a little bit of an analogy for you. I'm sure that you've ordered items from Amazon or from other online stores, and maybe 15 years ago when they started commonly providing tracking websites for your orders, you would be checking the website. Let's say you were really looking forward to something that you ordered. You're just checking the website and you're clicking refresh, and then you have to go to work and you come home and you're clicking refresh again. But you're making manual requests, outward requests. But then they came up with the idea, hey, we can send you notifications on a tracking app. That's what a Kubernetes controller allows us to do, is our API, instead of running a schedule every 15 seconds requesting all of our workloads and then updating the database, we can actually just have Kubernetes controllers running there on GKE for us, telling us when the state of something changes, which is really powerful. And that's exactly what we did. We actually wrote a custom controller called Workloads Controller. And we're still working on it. I think work on things is generally endless in software. But it's working reliably so far, and we've actually delivered it to prod. So if you are a cloud customer and you go on the Cloud Console right now, your state updates, everything that's updating is coming from the Workloads Controller. And we're really excited about it, and we're glad to show it to you today.
So let's review this architecture a bit. So before we started with decision on running the polling mechanism with the scheduler, we were every interaction reading from all of the clusters, all of the workloads. This posed many problems as I talked to you guys, adding latency in case we add more customers to the data, right? But also wasting a lot of resources because as we discussed, data changes are unpredictable. So there were many times where the scheduler was reading a state from the cloud, but the state hadn't actually changed. And that was just waste of resource. We were wasting compute and memory and all of that to read the state, but the state hasn't changed, right? So why not move to a smarter way of doing this? So the workloads controller works this way. So we have the workloads controller deployed to each one of the clusters, right? It's running there. It's hooked into the Kubernetes control plane life cycle. So every time you make a deployment of a service, a build and a deployment, our API will notify the Kubernetes cluster. Kubernetes, as Jared explained, will make that state happen. We'll create the pods, we'll update these pods, and all of that. And we'll notify the workloads controller. Workloads controller will see this event happened. So, for example, the service Liferay has been updated from 2 replicas to 3 replicas, or the Liferay is having a new deployment. So the workloads controller will get that information right from Kubernetes and in real time, right? And we'll be able to send, that's what it does. It basically sends that information, that event, to our API, which is then able to make our cache in sync, but now with a great difference. Real time and not wasting resources. So the sky is the limit. There's much more that can be implemented with Kubernetes controllers. The workloads controllers is just the first controller that we implemented. There are many other use cases where we are considering and already discussing about the architecture of controllers. And you can perhaps, if you use if you use Kubernetes, you can also think about use cases where the controllers will help you to solve problems. There are many open source controllers that exist nowadays as well that you could be using for you. But yeah, hope you guys enjoyed all of this experience that we shared with you.
Yeah, we'll be around. So if you see us, ask us about nerdy things. And take it away, Wes.